Yeah, that's right. But
And just hide this interview so we know what's
you're going to be standing there, right?
So we're starting now. Sorry for the delay. Um,
So, hello everyone. I'm Deep, and I'm the team lead for PurdueFW Lunabotics project, and we are representing Purdue University in the NASA Lunabotics Challenge of 2026. So we'll just go over through our system design review session. Welcome everyone. We'll go over through robot overview proposal of what we are planning to design by the end of the project, excavation system of the robot, deposition system, drivetrain, hardware, autonomy, business and operations, and concluding remarks. So let me introduce all of you to the team and the Lunabotics Challenge 2026. So the Lunabotics Challenge is basically to construct make and design a construction robot which excavates regolith from excavation zone and deposits in deposition zone. It's a basic university level competition organized every year by NASA, and teams are required to organize themselves and work together to make sure all the rules and regulations mentioned in their guideline are satisfied. There is a qualifier round in the second week of May, and then in that qualifier round, the NASA we have to travel to University of Central Florida, and over there they check whether our robot actually meets all of the requirements and it actually performs all of the tasks which is meant to do so. Then once the qualifiers are done, top 10 teams are sent to Kennedy Space Center in Florida, and over there they compete with each other in terms of autonomy, in terms of object detection, in terms of how autonomous or like how efficient the robot is in terms of power efficiency and all other aspects which are defined in the guidebook. So here is our team. I'm the team lead, and one by one, everyone's going to introduce themselves.
I'm Swag. I'm Swagat. You can call me Swag. I'm the drivetrain lead for the mechanical engineering team.
Our telemetry and control lead Arnav is not here, but he is in the he's in the software team of telemetry and control.
Hi, I'm Shaurya. I'm in the software team and I'm leading the navigation part of the project.
I am Vishal Parvekar and I am like doing the mechanical design part of the project.
I'm Amit. I'm the lead of AI and perception in the software team.
Prem, he's in the testing team. He's the testing lead for the team. And yeah, Shruti is documentation lead. Testing and documentation are a combined team, and she's the lead for documentation.
And I'm Vance, and I'm the electrical design lead.
I'm Tia and I'm the media manager.
We have Samya, who is the systems lead, and she's a part of EC team.
Then I'm Akshat, and I'm the firmware and system team.
And we have Dr. Liu as our official faculty advisor for the Lunabotics project. And our first sponsor for the project is Philride. We have John from Philride here as well. So we'll just start on with the presentation, and first is robot overview.
Okay, so from what we had planned, that's the mass allocation. So for the excavation and deposition systems, we had allocated around 16 to 17 kg of mass. That's well within the values we had decided in the PMP, the project management plan that we submitted to NASA in the initial phases. In that, we had set the mass to be around 20 kgs, but it's well within that limit. For a drivetrain, we have around 25 kg of the master subsystem, and the lateral system comes out to be around 10 to 15 kgs. Next. Okay. So the technical performance measures were derived. They were derived from system requirements, and those were obtained from the guidelines and a rule book given by NASA.
So during the creation of our PMP, we had to come up with a set of measures that can help us determine what kind of robot that we would like to design and how we go about designing it as well. So for our robot, we mostly decided to go with to focus on designs that are energy efficient, and we're trying to focus on autonomy as well. So designs that can function best under autonomy, so not too many variables that will have to be under consideration, and or something that's more simplistic, as we're a first-time team, so we didn't really consider designs that are too complex or too unexplored.
That's a list of the technical performance measures that we had like submitted during the PMP. And yeah. Okay. Now we'll go ahead with the designs we had thought of and the ones we are going ahead with for the project. So during the brainstorming phase, we had multiple ideas. Some of these were the excavator with elastic tube. It worked as like a basic industrial excavator. Only the difference is when during the excavation part, the scoop will just lift high up, and the funnel tube at the end of the funnel, end of the scoop, will just make sure the granulate passes through the tube and gets stored in the storage. So the pros is it's based on modern machinery and its tested method, but the cons was the high energy consumption to lift the scoop high into the air. So that's why we scrapped that idea. Then we had an auger system. This again pretty based on modern machinery. It has very low scope of failure, but it's time consuming because the speed of it depends on the angle of the ladder as well as the angular rotation, angular velocity of the auger as well.
We'd also come up with a sweep type system, essentially a robot that functions like your household, like scooping and broom mechanism, if that makes sense. And we discussed quite detailed with that specific proposal in the beginning because we thought it had a lot of scopes. There's the only thing is that we had way too many variables to consider with that design, and also making it into a functional robot on such a different type of sand was something that we decided not to explore on. And we'd also that had led into a dog digging type of robot idea, where essentially it has claws, as we like to call it, and it just pushes in sand into a storage, which then gets carried to the deposition zone. This system worked on principle. It was, I guess, because it was an excavation system that that was used sometimes in the industry as well. But because of the sheer complexity of the design and I guess the scope for failure was kind of high in that as well, we also decided to move in a different direction from that design. So we had shortlisted by the end of it 2 different designs. So one is a bucket ladder system, one that it essentially works like a conveyor belt. So there's this specific mechanism which descends down into the sand, and it starts rotating a bunch of mini buckets which scoop up the sand and drop it down into a storage system over there. This design idea is the most widely used design idea all throughout the Lunabotics competition. Most teams that are starting out, they choose a design like this because not only is it well explored, it also has tried and tested methods which we know. So even though it is a complex mechanism with a lot of moving parts and a lot of scope for dust to infiltrate inside the different components, it was something that we knew how to work around, or we could at least find methods that could be used to work around.
And then I like the dog dig system, and I really like the front loading scoop, but there were inefficiencies to do with the storage. Namely, the tube goes right through the middle, which means that this space is not used as storage. How we would dump that was also not super clear. So I proposed that we push the scoop from the front, where it would offset over mass. So we'd have a lot of mass right at the front, but topple over, be unsteady. So I proposed that we put it in the middle, and that the scoop goes back around, and then it comes with. And it would just scoop it from the interior in between the wheels.
So as mentioned before, this is a more detailed explanation of what we were intending on using the bucket ladder system for. So obviously it helps with getting a lot more sand in one cycle. It also helps with just improving overall efficiency as it's a set system. It's easier for autonomy as well, as autonomy could be more focused on stepping away from rocks or craters or something. And since it's just a rotating mechanism that has to be executed, it was something that was beneficial for our discussion and something that was worth considering. Also, we gained a lot of insight and tips from the main campus team as we had gone there to visit and get a bunch of bounce ideas off of them and discuss general topics relevant to the competition. And they're also using this specific design. So having someone that's so close by and that's giving us so much tips, really pushed forward this design for us. However, considering the fact that we are a first-time team, creating such a complex design with not as much time as we would have wished that we would have had, and also getting the correct parts that could make the robot function perfectly, was a discussion that the ME team felt was, we thought that it was a bit difficult from our side, from the team side to execute. However, the tried and tested methods for this design, as well as its pros, definitely made it something that we really consider deeply.
So for an internal loader, like as Chase said, that's what the mechanism is. So basically, the bucket will be in the center of the robot. The central space hole completely allocated for the excavation and deposition system. So the system works by just the excavation cycle will just run in like one rotation of the motor or the input crank, in which half of it will be allocated for excavation and the other half for deposition. So in this case, the pros are that there only one mechanism for the excavation and deposition both. So it's pretty easy to automate as well, and with very less mechanical complexity. However, the cons is that it can't do it can't collect sand multiple times in like one cycle of excavation deposition. Yeah.
So if we do get a really, like, if the robot during autonomy gets a floor scoop and it's only able to gather a very small amount in its little storage, we can't go back again without dumping all of the right-of in the process. So that's the main drawback. Thankfully, it only runs on one motor though, as compared to the bucket ladder, which requires multiple actuators and motors. Yeah.
Okay. So for the excavation system, we had like these mechanisms. They considered these mechanisms to define the path of the container. So one is the 4-bar linkage, that's that image on the right. The 3-Janssen linkage mechanism, and the Cartesian path generation, that just works by using two linear actuators perpendicular and like using that to generate the path, and the cam follower mechanism. Okay. For the 4-bar linkage, basically this will satisfy the Grashof condition for the 4-bar, and according to the study done by and the simulations done on SolidWorks, we got these values of motor torque. The torque requirement was around 150 Newton meters. Consumption was around 120. Maximum consumption was 116 watts, and total mass was coming out to be 11.5 kg. These calculations were done with the angular velocity of the motor to be around 10 radians per second, and the load in the container to be around 73 kgs. And that's the animation. So So that's how the path of the robot will, for the container will be. So it scoops during this phase and it deposits like this. So just a second. Yeah, so once it excavates, um, we'll have a latch system to hold the mechanism at this point while it travels to the deposition zone, and then like continue the motion to like complete the cycle. That's what we had in mind for this. Chase.
And then, as opposed to the 4-bar, we also considered the Jensen linkage because it has a very nice flat curve right here. So the bucket would sit in a very settled position. The concern was that we wouldn't be able to, the height of the Jensen linkage and just the sheer size of it means that for such a constrained space and such a big bucket, we were worried about power requirements. But we were able to modify it with this addition to keep the tilt relatively tangent to where we're going, so that when it goes to scoop, it's always moving or it's always angled in such a way that you wouldn't shuffle. Here we see the bottom right part of the bucket and the this is the wrong one.
So these are basically the
This is what
multiple
I
like link lengths that we use to like just play around with the path, and the best part that we found was, yeah, please, okay. Just a minute.
It was this right here.
Yeah.
And so it has one big bar that goes around the back and controls the angle.
Here's a simulation for the best path that we found for the Theo-Jensen linkage. Again, it's the same mechanism. During the digging phase, it will work and then stop at this point until we go to the deposition zone and then continue the cycle for deposition. And the other solutions we had, that was like the Cartesian path resolution system. It basically works like how a 3D printer works. So it just used two linear actuators placed perpendicular to each other on a frame to generate the paths of the storage system. Then the other one's cam follower mechanism. We'll have to design a custom cam follower for to generate the motion, but we couldn't get to that because of time constraints. Now for comparison between the internal loader and bucket ladder, so for data for a bucket ladder, we just reference data from the other teams who have used the bucket ladder already, because it's a generally widely used system. So we thought that we could just use their system, their data for comparison. And if we go ahead with that idea, we'll improvise with our own values. So the value we got for the internal loader is around 52 kg, while for the bucket ladder is 20 kg for the maximum mass collected. And that's the whole data for the comparison. So basically, the number of components for the internal loader is generally lower than the bucket ladder, except for the Janssen linkage. However, in this case, the connecting links are pretty light and the connections are pretty straightforward. So they shouldn't have much problem in like assembly.
If you subtract 18 from that, because some of those bars are actually singular blocks, so they don't need to be like they're rigid structures. So you don't need multiple bars, but that can go down to around 10.
Yeah. So basically, in this case, this triangle is one block, then this triangle is another block, and so on. So that reduces number of links as well. Yeah. Also, that's considering the links on both sides of the container. So that's why the numbers are like twice the size. Yeah. And the motor placement for the links for the systems are mentioned.
For the mass of each component for each system, we were thinking that the internal loader will be able to get the total mechanisms of the excavation for around 11.5 kgs, including all the links, and the storage that would be consumed. And the deposition system overall, based on research, we found out that the bucket ladder can depose around 13 kgs worth of regolith. And for the Theo Jansen linkage, we estimated around 12 kgs, and as opposed to having total of 31 kgs for the bucket ladder. So overall, we were looking for we were comparing a design that's one is more mechanical in how it works, and another one is more based on how it's the motor components or the electrical components work in tandem together. So for the drivetrain, we were thinking that we would use a common drivetrain between any sort of regardless of the design for excavation that we had. We were thinking of using a common drivetrain, and which would involve 4 wheels. So we were looking at 2 different types of wheels for now. One is a standard lunar rover wheel, which is essentially designed to run on basically a surface that doesn't have much gravity and easily compresses and decompresses itself alongside how the ground is. So the type of sand that's going to be present in the actual competition, so the type of sand that's required for us to move is a sand that's called BP1. BP1 is a chemical sand that NASA has themselves, and that sand has the texture of flour. So as the robot moves around the entire zone, it's going to be changing the structure of the zone as it goes around, including when it picks up sand. So our tires are pretty important as it has to accordingly adjust to how the terrain moves as well. And as we mentioned, we were thinking that we would place the motors towards the rear side of the entire component of the chassis, so that we could use a type of all-wheel drive system, so that there's a chain linkage within the chassis themselves that moves the tires on each side. And we were also thinking of a skid steering system. So a skid steering system is essentially when rather than you have the front and back of the robot moving together, you rather have the left side and the right side moving together. So it makes turning easier for the robot in tight spaces, which is why it would be easier for us to use for the drivetrain.
It also works really well with autonomy because it's a zero turn, so it doesn't need to move forward, move back. You don't have to do a bunch of control theory stuff in order to get it to traverse. Additionally, because the center is hollow, or because the bucket is in the middle, we don't have to turn around in order to return. So when we go to the burn and then to the excavation, we don't have to turn around at that point and then drive this way. We just reverse the motors. And so that was a really big thing for efficiency, because you see a lot of slipping and bearing itself in the competition.
So the EC team's ready to take over?
Okay, so for the electrical system, this is firstly the system architecture. So it's pretty self-explanatory as it reads, but I can go through it. So we have the robot, and then everything connects to the battery, and everything has to run through an e-stop. For the e-stop, it has to be, per the rules, 40 millimeter diameter and red. So it'll be that. And then it goes to the power distribution board, the PDB. So this powers, firstly, the Jetson, and then the Jetson is connected to the different sensors we have here. So situational cameras, real sense cameras, possibly LiDAR, depending on the design. And then you can follow this over here to Wi-Fi, which is required to communicate with the robot. And regarding Wi-Fi, for everything related to bandwidth, it's generally our approach, and it was recommended by the official rules as well, for it to be as, it uses little bandwidth as possible for like reliability. And then this is the Mission Control Center over here. And then the Jetson is also connected to UWB, which will be an Arduino.
The UWB will be used for positioning, and then the Jetson will be communicating with the TNC using serial USB, and the power distribution board also powers the motor drivers, which will help control the drivetrain, excavation, deposition, and other miscellaneous like motors or actuators that we might need depending on which deposition and excavation method we use.
Yeah, and the TNC will be powered by the Jetson through the USB because it requires very low power, and then the PDB powers the motor driver, which in return powers the drivetrain, and then also all other motors or linear actuators that may be used depending on the design for excavation, deposition, and then miscellaneous generally falls in for actuators.
And then the PDB also does have a data logger for energy usage, current usage specifically, because one of the factors that we will be graded on is energy usage, and also another thing would be how much bandwidth we use. So that's why we're trying to use as little bandwidth as possible. So during autonomy mode, we'll probably have as little communicating with the mission control center, just enough that we can know that the bot is operational. And if we turn to manual, then we will make full usage of the mission control sensor with all camera streams and being able to use Xbox controller to control the robot.
Where is it? Okay, so for the power distribution board, I have two parts, and I am referring as this is what I'm calling the low voltage system. I put in quotes because it's really not a big difference. We'll get into it in a moment. So we will use buck converters. The reason for buck converters opposed to a different form of stepping down the voltage, such as a linear regulator, is simply due to the efficiency of MOSFET. So we're using two because we have Vout 3.3 volts, which is for the sensors, and 5 amps is very overkill for that, but it's for consistency's sake. And then 5 volts, which is for lots of the microcontrollers, so the Arduino and the Jetson. So it will also include the e-stop, as I discussed. So this is a rough drawing. I'll explain. And the e-stop, as I said before, 40 millimeters diameter red, and for peak current for everything, assuming for the internal internal loader for the design. So for the internal loader, it requires much more current, approximately 20 amps on the high voltage system, which I'll get to in a moment. But so that'll be located there, and for a sufficient buffer of approximately 20%, it'll be rated for 50 amps, which is not what we'll be using regularly. However, that's just for peak for startup, and that's from the simulations from mechanical team. And then for data logging, we'll be connecting like those 7-segment displays that have built-in voltmeters to the system. We'll be connecting it, and also this is just for testing. These are test points here. We have test point, which should just read the 25.9 volt LiPo battery, which is 7 series, and we will have 2 of them, both at 5,000 milliamp hours. So we have a test point 1, and then test point 2 up here, which is for the this is for the 3.3 volt system, and test point 3 is for the test point 2 is for the 3.3 volt system. Test point 3 is for the 5 volt system. So we wrong. Yeah, I was correct. Okay, and that is all dependent on this resistor here, really, and the rest is just calculated from their data sheet, and the vSense is just on this IC, the TPS 5450. It is finding the voltage division. So that's the low voltage system, and here in a second, this is the high voltage system, which is unfinished, but I can explain it. And it is using the LM5170Q1, and the reason for that is because originally I wanted to have a system where everything was integrated into the ICs, similar to the TPS 5450s. However, there are none available, and it's just not very common for that. I wanted that for simplicity's sake, but that's not very common for the very high current peak we have, which is, as I said, around 50 amps. Well, 50 amps for buffer, so like 38 amps. So this will have a similar system. So this is so these are high current controllers, which require a lot more external circuits, and and for these, the data logger, so these will not actually have a data logger similar to these. Since these, the high voltage system is for the motors, is for the drivetrains, for actuators and everything of that matter, it requires much more current. So we have a 12 volt system, as shown here, and then for 24 volt system, and due to these ICs, due to their nature, you can control their current to quite a high margin. So their data logger, as I was saying, is controlled via Teensy, and the Teensy 4.1 actually has very, very good data logging capabilities, and so we will program it in such a way that it will be able to we will be able to receive live from the mission control center RPM, current, power, PWM, which is the PWM for everything, and then the motor status, whether it's active or not. So that's effectively that. And one other thing I did not mention was the ENA inputs. So the ENA inputs are an alternative way for an e-stop backup system. So if it is half a volt or less, then it is assumed off. So there will probably be that wire for each of these, and then a similar system will be found over there. And for the motor drivers, for the motor drivers, they will also have a redundancy e-stop system so that they do not abruptly stop. And
so for motor control, we'll be using the Teensy 4.1. Part of the reason why we're using the TNC is because it has a high amount of PWM pins, specifically 28. Also, originally we had thought to use Jetson or Nano, a Raspberry Pi, and then a TNC as a way for like vision, control, and then motor control. But we realized we could just get out the Raspberry Pi because this has enough processing power for motor control, and we could have the Jetson or take control of the like robot automation. So the TNC will do the entire grunt work of that. It's will output high and low voltages as a way of telling the motor to start and stop, which will communicate with the motor drivers. The motor drivers, since the motors are 24 volts or 12 volts, and this only outputs 5 volts, so we have to use motor drivers as a way of actually having the motors move. And it's also very low power consumption wise, the TNC 4.1 compared to the other TNC board versions. So that's also a big reason of why we're using it. There is one problem is that depending on which kind of motors we use, brushless or brushed, how we connect the TNC to the motor driver will be different, because if it's brushed, then we can easily use a standard saber-tooth motor driver with PWM controls. But then if we want to use brushless motors with which have Hall effect sensors, we would have to make our own motor driver boards, which would be slightly costly, but manageable, and probably about $50 each. And we could figure out a way to have PWM work with the brushless that way.
Yeah. So this is the motor we chose for the drivetrain based on all the power ratings, torque ratings, and RPM which the mechanical team developed. It's a brushless DC motor, and it has like it's a 3-phase motor with 3 Hall sensors, and then with yellow, white, and blue. And if this is the basic data sheet which tells you like what are the specs of the motors with given gear ratio to be of 50, and efficiency is 75%, which matches our power efficiency aims or goals. And also it's basically it's a high power motor. It's around 220 watts power rating. That's why we chose this, considering the load on different designs. Once it's like normally the design is going to be, or like the drivetrain and the robot is going to be around 20-30 kgs, for example, but the load is going to be 30, 40, 50, and sometimes 70 kgs. So depending on the highest load, that's why we have chosen a high power rated motor for the drivetrain. And there can be 2 of these, one on each side of the drivetrain, and then one motor will drive 2 wheels through a tank thread system. Now, the main thing which we were looking forward to was a stronger GPU. Like Akshat mentioned before, we were trying to check out a system where the Jetson communicates with a Raspberry Pi, and then the Raspberry Pi is responsible for the control and navigation. But when we did some research and we talked to other teams, we found out that the Jetson should be capable enough to do everything. The Raspberry Pi will simply go add on more power requirements, which goes against our goals for being power efficient. So we have 2 comparisons for Jetson Nano and Jetson Orin Nano. Jetson Nano is a very basic, kind of like a hobbyist GPU with like a 128 core Maxwell GPU and a quad-core A57 CPU, 4 GB RAM, basic AI, basic object detection models, and all those common features which nowadays even high schoolers do. But since this requires a very strong navigation and AI perception system, we were thinking of migrating to Jetson Orin Nano. We were provided the Jetson Nano through the ECE department. That's how the initial testing began. But right now we are planning to obtain a Jetson Orin Nano because it has a very, very high computational power as compared to the Jetson. If you compare like the first parameter, 0.5 tops, and this one is up to 40 tops. Jetson Orin comes with an 8 GB or 16 GB RAM, so it's very, very efficient in terms of memory mapping. Its use case supports YOLO V10, which the computer science team or the software team will cover more in detail. But since we need a very strong AI system or like AI object detection system, Jetson Orin Nano will support the software team's goals. Apart from that, it supports basically all common perception models like the SLAM, NAV2, and it's commonly used in robotics. That's why we're aiming to move forward with the Orin Nano. Then we have the mission control center. The mission control center is basically responsible to when the robot is in autonomous mode. That time it's responsible to track all the data from the robot so that we know what is happening in the pit. But whereas when it's in semi-autonomous or completely manual mode, that's when the mission control center will have a huge role, because the students in the mission control center will be responsible to control the robot using Wi-Fi. So we need a router, we need a laptop, a monitor, and an Xbox controller. Xbox controller supports basic controls over Wi-Fi. So yeah, that's why we need a separate system for the dedicated for the Wi-Fi.
And then, so the Jetson Orin Nano will also be communicating with the cameras. With the cameras we're planning on using for navigation purposes will be specifically real-time depth cameras. We did consider the Z2, which is used for the boat project, senior design project, but this is more well documented because it's a more used brand in stereo vision research, and it also has inbuilt IMU, supports multiple resolutions, and has a high frames per second. The field of view is about 78 degrees, which is really good. And we also have, it's easy to communicate with the Jetson or the Orin Nano because it only uses a USB as a way of communication. We will be using two of these, one for the front of the bot and then one for the back of the bot. The reason is because we want to minimize turning for the bot as much as possible. So it'll travel one way using one sub camera and then travel the other way with the other. We will have extra cameras for situational awareness that will be used only if we turn to manual mode, which will only happen if autonomy fails. So that's the camera vision systems. And then to help with the autonomy, we're going to be using a UWB positioning system. The reason is because it's a real-time location system that allows for more accurate positioning of the bot rather than just using camera pose estimation of a SLAM environment. If we were to use UWB, it might not just reduce but completely eliminate the need for camera pose estimation. Along with IMU data, we can use it as a way of accurately placing it in the environment. So the reason why we're thinking of UWB, it requires like anchors, which we are given anchor points on the starting point of the field. So over here where the robot starts, the wall here and here are going to be lined with mounting areas where we can put the anchors, and the tag, which is the UWB tag that moves, that's we'll be able to communicate with them using time of flight calculations and then also a moving average. We can get an accurate distance from the start zone and where the bot is. And in relation to IMU data, we can get an accurate position of where on the field it is. And why we also have the option of using laser, but why laser doesn't work is because the column might get rid of line of sight. And if we use a light-based system, line of sight is mandatory. While UWB, which is a radio system, doesn't always require line of sight. So, and UWB compared to like a light system is also much cheaper and much less intensive on power usage. So and also the one we're probably thinking of using is the Arduino Stella, which uses D150 chip rather than the standard Qorvo DWM 1000 or 3000, because we want, while it is less range than a DW1000, it does have higher response times, and it also has a built-in IMU, this one, so we can use it when we're testing. We don't necessarily have to be dependent on the camera's IMU when we need to individually test it. So, yeah. And then CS team will be going down to talk about toggling.
So software team is basically the brain of the robot. We manage all the functions of the robot from deposition to excavation to moving of the robot. Our architecture is based on a hierarchical structure where ROS is the backbone of our middleware. And briefly touching upon ROS, it is basically the robot operating system. It is a standard operating system used for any robot. It has nodes which are like 35 to 40 nodes, each concerned with different functions, and each have programs. Each program, for example, the camera node, it takes pictures and it posts to the bulletin in the ROS, and each node can take outputs of other nodes from the ROS. So basically, it is the middleware of our system, and it is our architecture is basically 5 layers. Arnav will walk you through the layers.
So as you can see, it starts off with getting data from the sensors. So we're using a combination of both RGB camera and LiDAR. So both of that data goes to the perception, which is basically the YOLO V10. After that, we also use the data from those devices for localization. So from the RGB camera, we go to the we get visual odometry, and from the LiDAR we get point cloud matching data, and then from the IMU as well, we get data which we which we do sensor fusion to, and then both the perception data and the localization data goes to the path planner, which uses nav2 to create a route, most ideal route.
Yeah, so basically, nav2 is a framework which we use for path planning. It takes data from various parts in our system, for basic perception and all the sensors, and it creates the best path, which we will touch upon in the later slides, and it gives the output to the motor controller, which will in turn actuate the drivetrain for the robot to move autonomously.
Like so on the slides, the second layer of the system architecture is the perception layer. Here mainly our goal is to identify or detect objects in real time and extract terrain features such as rock, craters, the excavation zone, and the deposition zone. For this, as Arnav said earlier, we are using two input devices. One is the RGB front-facing camera, and one is the depth from the LiDAR. We are also using a YOLO V10 model, which will be trained on a custom compact dataset. The dataset will include images from like the team said, the DP1 lunar regolith. So it is trained on the correct domain for more accuracy. we initially merged these two images from the RGB camera and LiDAR. We do some feature system on them like normalization, and then we transmit to YOLO model. The model detects objects, it makes bounding boxes on them, and then it is then forwarded to the tensor RT. Tensor RT here is mainly used for real time, so we can have high accuracy from YOLO and also achieve a real time from the tensor RT. Next, we put this results in ROS. So our next layers such as localization, path planning can use this data. Localization and mapping is one of the very important layers of our project, since it is very important for autonomous navigation. We have broken this down into 6 components. Sensor fusion. We integrate the data from IMU and the vision autometry. We get a probabilistic estimation on these. Since we need to find paths and we don't know what the next steps are, use a probabilistic estimation to get a more accurate data. We then move on to the coordinate transformation. We maintain consistent sensor frames using the ROS TF2. There are multiple frames here. What is going to be from the LiDAR, what is going to be from the camera, what is going to be the base frame which the robot will be moving on. Next, we go to the slab algorithms. Here we build real-time maps with occupancy grade systems. So when the robot is moving throughout the arena like you saw before, it will detect rocks, craters. Now, since we don't want to waste time, we store them on a grid, so we know where the rocks and craters are. Next time when we are moving around, we don't need to waste time wandering looking for objects. We can find the best path going forward. Our environment model places a semantic object detection on this grid map, so we know where the excavation zone is and where the deposition zone is.
So our next part is path planning and following. Basically, path planning is where the robot transforms from high-level functions like excavation and deposition to basically navigating throughout the arena. So here it's basically divided into 2 parts. The inputs to this node will be basically the robot pose from localization, which Amit spoke about in the last slide, and the obstacle map from perception, which we will record from the sensors and the camera. And then our algorithm, which we are planning to use, is the Distra algorithm, which will plan a global path, which is the best possible path, which will make the robot move in a very efficient manner, minimizing the power and complexity. And then we also have the dynamic window approach, which will dynamically change the path of the robot based on the newly detected obstacles. And it will also keep in mind the kinematic constraints of the robot, because it is a 70 to 80 kg robot which cannot move dynamically. We have to keep some margin of error for the velocity and things. Okay, so sorry, the last part is the PID control, which is the control layer where it will basically transform the desired velocity to the motor drive commands, which will in turn actuate the drivetrain and make the robot move. A very critical part of our path planning is the operation modes. We have basically 3 modes. The first is the autonomous mode, in which the planner will function on its own without intervention from the mission control room. The second is the semi-autonomous mode, in which the mission control room can intervene and basically give path planning directions or velocity commands. And the third one which is the worst case scenario, is the teleoperation mode, in which we will use joysticks to give the directions and velocity.
So fully autonomous gives us the most points, and semi-auto and teleop modes are going to be fail safes in case autonomy doesn't work out as we plan.
Yeah, so basically this was the software part and the business can take.
So for business and operations, our main focus is, first of all, was outreach for basically start a first round of fundraising, and that's when we contacted different departments. I contacted my senior design project sponsor, and through which we got initial funding through Philride, and we are still in talks with different departments so as to how they can help us with. So our proposed budget was earlier to be around $9,000, including all mechanical parts, mechanical and electrical parts, and even some software packages like GitHub or any GitHub and a storage AI cloud storage system. So right now our budget stands at 2,397, around $2,400. This is way less than what we had initially proposed during our project management plan. Uh, this is majorly our entire hardware side of the project, which involves all the motors. Not all, technically all the motors, but basically whatever we have right now, we want right now, which will be the motors, the sensors we require, and the Wi-Fi setup and the power distribution components. So the power distribution board is around 258. That's because it's going to be a PCB, and it will have different ICs and like ICs and like resistors, capacitors, inductors, all different components. So the entire budget for the power distribution is 258, and we need two of the 25.9 volt lipo batteries because of the motors which we are selecting, because our motors are going to be 24 volt motors, and the alternate DC gear motor for the excavation system, it's rated at 48 volts. So for that we require a complex like a two battery system for our project. Then our next steps would be the preliminary design review based on the chosen design. So we did the system design review today so as to get inputs and feedback from our faculty and all the team members, so that it will ensure a smooth and efficient way of choosing which system we should go forward with. Once we have the design ready, that's when we'll move to the preliminary design review, when we will begin a complex research on how the system is actually going to look. Then we will begin the phase 2 of fundraising, since we have been able to raise only $1,000 right now. And also apart from that, like a lot of our team members have some sensors, some microcontrollers already available, while some components have been gifted to us by the ECE department. So all of that was our first round, and now in second round we will need to buy all these components which was in the proposed budget for the system design review. And that's when the actual design of the drivetrain will begin, which is in second week of January, because our critical design review is scheduled according to the Gantt chart on 2nd of February. So before that, at least we want to start designing the drivetrain and have at least the power distribution board ready, so that we can critique the design which we currently have. On top of that, we are planning, since we are like 3 months behind time, that's why the critical preliminary design review it will be scheduled during the break. We're 2 months behind schedule, my bad. But the preliminary design review might be conducted during the winter break, because if we don't, we can't really stop working on the project over break, as the time doesn't allow us to do so. In February, after the critical design review, we have to do a proof of life, which NASA requires us to do so. And in the proof of life and a media release, we have to show what we have actually worked on, so they know that we are actually making some progress in it. And at the same time, after the critical design review will be our third phase of fundraising, and testing will start as soon as we start building the models. So the third round of fundraising would be the last required components which we need for the robot, and the drive by March end to April, we should have a first prototype of the entire robot ready. So right now, what we are aiming from you guys, we are towards the end of the presentation, is help us choose a design which the mechanical team proposed. One was the bucket ladder design and was the internal loader design. This is because if we have industry feedback, if we have expert feedback, that will be better for us to judge these designs and also give us a lot of insights on how the preliminary design review is going to look like. So it's all on you guys. And we'll have our team members to give some concluding remarks, all from EC team, ME team, and CS team. So the teams are going to just give you a just a very small summary of both the designs which we have proposed, so that you can help us identify which one to choose.
So the summary of the ideas we had, like the shortest ideas is, one is the internal loader with the scoop in the center of the robot itself, and the other is the bucket ladder. So let's go back to those slides. Yeah. So yeah, that's the bucket ladder system. The Sven, can you take over?
Oh, yeah. So, as I mentioned before, the bucket ladder system is it's an efficient working design of collecting sand, and the only concerns that I would have for this design would be first the level of complexity required to actually build a working model for this design, and just concerns of how technically knowledge we are to make it. But the design itself is the most the most used design in Lunabotics, which I really like. I guess it's a tried and tested method which can work well.
You see,
For the internal loader, we have like multiple systems for the mechanism for the path generation. So we have these solutions designed, like thought of. So one is a 4-bar crank rocker mechanism. The other is a Theo Jansen mechanism. The two linear actuators, Cartesian path generation system, and a cam follower mechanism. Yeah, that's it.
Okay.
PC side.
Okay. I want to mention one thing regarding the bucket ladder. It requires much less power because there's less motors. So that's another thing to consider. But I'll be fair, the rules do not count many points. I believe it's 40 points out of a total of 650 points for power efficiency. So it is not a top priority. However, it is something to consider. So so for the rest of ECE, for like a summary, as for the power distribution board, basically we're using 4 buck converters, 2 different types, and they are to distribute power to the whole system. It includes data loggers, it includes e-stop systems, and that's it.
CS.
For the CS team, mainly a lot of them had CAD models to show or some kind of images to show. For a CS team right now, we don't have anything much to show, but not like them. They, I think, start building the robot in February or later January. The CS team has started working on the models. We will start our integration and testing soon by end of Jan or early February. And we have been told that if we can get this autonomous track ready, we have the chance of getting highest points available.
Yeah.
So.
As it is a SDR meeting, we are here to decide which design we are going forward with. The software team is not really concerned with which design we go forward with as much as other teams. But as long as our perception sensors and camera are in place and we get the data, so we will be able to detect the autonomous part.
Since autonomous, like being fully autonomous has the highest weightage in the entire grading scale, around 400 points.
600.
600 points? Okay, around 600 points. So that's why we are aiming for a fully autonomous robot. We are not right now we are not going to focus on the semi-autonomous and other modes because that's what we are going for. And then as we move forward, once we have that milestone achieved, that's when we'll move on to the other modes to make sure like our robot is failure efficient in just in case, since the chances of failure, like there's not a single team in the last few years who has achieved full autonomy, but that's right now we are going to
That's
revolutionize
why it's a
that.
great motivation to
Yeah.
get it working.
And to be clear, so it's not an out of reach idea.
Yeah.
Many schools, including Purdue main campus, got extremely close to achieving full autonomy. But if there's just one small thing that goes wrong, they do not get the full points.
Yeah.
That's because a lot of teams haven't traveled with the idea of using AI or machine learning
Yeah.
for this project. They've used the stuff like cost max and stuff like that, but they haven't really gotten into using
Real time.
Yeah.
real
Deep machine learning models or something like that. I think this time we have a very unique approach and simple approach also. So
That's
we can
one
give
of the
this.
few teams that are doing.
Yeah, our fundamental goal is for both the mechanical and electrical team, is to make the system as simple as possible. We had a lot of systems at the very beginning, but we stripped down a lot of them because we want to make it as simple as possible to basically enable the best possible model from the CS team.
Yeah. We do not want to overburden them with a lot of things.
That's partially the reason why we also chose skid steering.
Yeah.
Because
Yep.
we found one of the energy efficiency wise, there was a lot of slipping of wheels if we used skid steering, but so there was a better steering system, but that wouldn't work well with autonomy. So that's why we were like, it would be better for skid steering, and we wouldn't mind the loss in efficiency if it means better autonomy.
Any questions from?
How much mass is supposed to be excavated?
70.
So it's capable of 85, but our simulations are currently for 75.
The way the final measurement is made for how much sand is moved is it's going to be measured just based on the the volume of sand that is there in the location where the sand is supposed to be dropped. So at the end of the day, it's just our best attempt to get as much sand moved compared to the other.
Actually, the points will be calculated by the volume of the sand divided by the weight of the robot. So as less weight you can put and like as more volume of sand you can collect.
So ideally, we shouldn't compress the permits and
Another question is there temperature considerations for this?
Yes.
Yeah.
Early on, that was really like that was a big concern. But because right now it's the team's understanding, but since it's going to be in an atmospheric environment, they don't have to worry about temperature like flight time.
But as you can see from the rule, this is from the rule book, a summary of the rule book. We have a maximum limit for the component temperature to be 85 degrees Celsius.
What about the ambient temperature of the environment that you're testing in?
We haven't been provided an ambient.
Because right now the rule book is still a draft technically.
Yeah.
NASA has not fully released the full rule book.
Yeah. They keep.
But it's assumed to be pretty. Oh, room temperature?
Oh, yeah.
Yeah, that was colder than room
Yeah.
temperature.
a little colder than, but ideally.
Yeah, in a vacuum environment.
Yeah, the biggest problem we have with temperature is we just want to make sure the Orin Nano does not overheat.
Yes.
So
Because we can't really. I mean, we can technically use the fans for cooling it down, but yeah.
we can use the fans, but we're supposed to assume there's like
There's a vacuum.
Vacuum.
vacuum
Yeah,
space.
that's what.
So that's why most pneumatic systems are open.
That Purdue's team did use fans, yeah.
Yeah.
Cooling it.
Yeah.
But we did have a plan in case we weren't allowed to use fans of just using the chassis of the bot as a big heat sink.
Yeah.
Is there going to be, once the design is finalized internally here, is there going to be somewhere for you guys to test similar to the V1?
So yeah, we were told by Purdue main campus that we might be able to use their pit if time permits and if we finish the robot according to the timeline. And also a similar simulation environment would be a volleyball court because the sand is all kind of almost the same. But apart from that, when we were talking to them, they said the consistency of the regolith is as same as flour. So we might have to buy a lot of flour so that and create a simulated environment.
But
with
they
it.
mentioned that a beach volleyball or sand
Sand
volleyball.
volleyball.
Last year, the last team that won was the team University of Utah,
Yeah.
and they tested out in a sand volleyball court. It worked out for them. So
Even the proof
Even
of
if it's more worst case.
yes,
Yeah.
there is a little bit more friction because the BP one is a little bit more
finer.
Yeah, finer.
Yeah. It's similar to flour.
Several questions. First, I have no idea about mechanical. So have you ever built that using the testing of this structure? It's still in C.
Yeah, we did simulations. I did SolidWorks analysis, and everything worked out according to the software. So
Can you do that using the
yeah, we can use that. We had
We're
planned that
planning on
before.
using main campus has a 3D printer that's more than just that it's more industrial level that we can use. So we're planning on using that. So by the end, I think we're supposed to get the final
Jan end.
Janet.
Yeah.
We're planning on 3D printing as many components as we can before we get them properly shipped. Just combining it all into one stick.
Yeah, because if you use the code, it's really with everything. Another thing is for the arena that they show some of the side where you want to test it here and when you don't, then you don't want to try to buy stuff there every day.
Yeah, the volleyball court.
So
But-
you have to negotiate with the supervisor all the
Yeah, we'll have to
I
talk.
think that's a later stage.
Yeah, it's a little bit later on, but another option is like literally like a pit of like flour, like like a big 25-pound bag of flour from like Costco or something we were talking about.
I mean, where you place that arena, it's 6 different times.
So I don't think so any team tests in that much space. Even the simulated arena which Purdue main campus is building right now, it's not even I don't think so it's those perfect
It's
dimensions.
only about this much.
Yes.
Yeah,
main
it's-
So
target,
it's only a third of the actual arena that even West Lafayette has
Yeah.
so far.
the main target while testing will be that does it run autonomously for 30 minutes? Does it perform tasks such as moving, turning, collecting sand and depositing sand? Does
Can
sand
get
fall?
the
Yeah.
boundaries.
And
Yeah.
if it doesn't skid,
And if
or
it gets stuck, does it kind of like get out of itself?
Yeah.
if it detects walls also, because if the robot touches the walls, we get disqualified. But if we touch any of the objects in the pit, I think we get 30 points off. So we need to make sure it doesn't touch anything in the pit. Yeah. And it doesn't skid, obviously.
Yeah.
Yeah.
So how well we protect the robot from sand is also something that they're going to use to judge it. So if when you're excavating or when you're dropping sand, if a lot of sand falls on top of the robot itself, you get points cut off. So when we're building the robot, most of it has to be dust resistant. All the bearings, any mechanism that we have, any like screws or everything has to be dust resistant, completely away from sand. That doesn't affect any component.
Yeah, and for the and for the PCBs, do a conformal coat on it.
Themselves have a dust cover on them, so they're supposed to be resistant.
Yeah, there's other things we can look at to mitigate that. Kapton tape over connections that we can't actually put a full coating on. Similar such measures.
A big part of the design as well. Another team has already done a similar internal sweeping mechanism, but when they went to dump, they would dump it right on their axle, and that version broke. And then after a while, it buried itself, and then one of the linkage beams just broke. The key thing is that the center is completely flat. So you can buckets on there. It's a frame that goes in and up of it. And easy stuff is kept on the side so that the regular never goes to the left or right. Additionally, Unfortunately, it's extended, so it goes beam, beam, wheel, wheel, overhead. So that myself, I had noticed that beams on the purely horizontal beams that connect the wheels tend to build up behind the wheels because the wheels dig themselves into a hole before coming out. We're working on getting a wheel design that won't do that for efficiency's sake, but it was just a big thing to keep right up on every. That being said, it's not a huge point category. We're just worried about autonomy and like power efficiency.
Because we thought more strategically that how can we earn the most points. So that's why we have chosen tracks which from where we can earn more points and with more pros and cons where we can lose points and we cannot.
Good space for you.
Right now, nowhere.
To build, we are currently using
ET331.
Tiny room.
It's
It's
a
a
very
small
tiny room.
Yeah.
Yeah.
All of us don't go together.
Yeah, I
inside.
think only 5 people at once can enter the room.
But we
And that's
but we'll be able to like store it in there at
there any-
least.
I mean,
Maybe.
until we have a space,
If
we
we-
won't be able to.
Are there any empty rooms in student housing?
That'd be a good idea.
Yeah, but then we won't have the tools.
Huh?
I might be able to give you some space.
Oh,
That'd be amazing.
That's the West for you.
was very open to talking to her. We had
Yeah, we didn't even know how time passed.
Yeah, they told us anything and everything.
And Westlafe is letting us use their Bechtel Innovation Center to do any manufacturing that we need to do for the bot because it's much more available and every machine is free to use there. So
And even
Maybe use the free.
yeah,
yes, yeah. They also provide some materials for free
that
too.
cut down our mechanical costs by a lot.
Yeah.
That's why at the CST they're asking
They have
for.
to source a lot of
Yeah,
materials,
yeah.
but manufacturing and
But I think 70-80% of costs got cut
Yeah,
down.
a lot of
Wow.
first-time costs we don't
Yeah.
have to worry about because we're able to use the innovation center. Yeah.
No, we are a part of
Yeah,
robotics.
we're still on the robots.
Yes. Yes.
Yes.
our plan is to build a club for robotics for next.
Year. Yeah.
I also failed to mention is we're currently all of the calculations for the mass of the robot that's interfaced on around 6061, which is okay, but we're really hoping like if the mass does get to a point as we continue designing and stuff like that, that it gets higher, we have a bunch of alternatives. Like we're planning on composites, whether that's carbon fiber or fiberglass. Yes, they're extremely strong fiberglass products. They're super.
Yeah, but given all of this, yeah, our kind of main thing right now is choosing a design.
Design. Yeah.
So, what's that?
Which one is?
Well, our team's a little divided.
I mean,
Yeah, our teams are
That's why we're
divided.
We're looking for unbiased opinions.
Yeah, these are the two ideas.
We did a bunch of analysis. The mechanical team did a bunch of analysis on the internal scoop because that was just our little baby. But the electrical team for motor considerations before we knew how many motors each design was going to take went with the bucket ladder for simple for design.
The bucket ladder, even though it's tried and tested, we feel that we need to do something more unique. with
Yeah,
that.
I mean, we always thought that we can do some kind of innovative solution so that we can beat others. Because if there are 10 bucket ladders, then we really need to have something really good in the bucket
And
ladder.
it looks just seems like we're copying last year's Purdue Lunabotics.
But some of us had different ideas, so.
Yeah.
For us, we think it's an inspiration, not like an exact copy.
Well, for a bucket ladder?
Yeah.
Well, no, no, yeah, no, okay. Yeah, but no, for the bucket ladder, there's a spreadsheet for the previous year, and I think it was about 80% of the schools did that design. Now, but the thing is, the Purdue main campus, when we were speaking to them, they were saying that they were all relatively different. Purdue themselves did this design, And yeah, so yes, and the reason in my opinion that is so well done, it's so commonly used is because it's a proven and I consider it a solved engineering problem.
And also in terms of autonomy, like something that's extremely well documented.
Yeah.
And like it's been well documented with autonomy too. It's much easier to troubleshoot, and so we won't. If we come into a problem, we know there's a solution. With our internal loader system, it's like we are to an extent flying blind when it comes to autonomy with that system. So that's why there's a split in which design which I use. One that is mechanically pretty good, but then in terms of autonomy, that is like simpler to
Efficient, yeah.
implement.
That being said, although we don't have data for the interior scoop, it has very few actions that it can do. It is scooping, or it's not scooping, and it's traveling, and that's it. So
Given the short time frame,
sorry.
given the short time frame that you have to show the piece, which one do you think you can do?
I would say
bucket ladder.
I would have both.
Because our right now our closest source, okay, we have lots of resources, but our closest one is Purdue Main Campus, and they literally they rolled one out to us, the bucket ladder design, right there in front of us. So
They're even willing to lend us their wheels.
yeah. So
I mean, yeah, I just think that can't be the only reason we move.
no, it's
The wheels can be used for any design.
Using the West Lafayette's needed system as a backup.
Yes. That's
Oh,
what we're
that's
trying to
a
go
good
for.
way to look at it. Yeah. So he's saying this thing.
No, man.
That's what I'm saying. Ask him.
But yeah, so what we're gonna do, at least going forward right now, is gonna build it step by step, because the excavation and deposition is gonna be happening later in the process. We need to make the drive train,
Drivetrain.
chassis, all that, and then maybe we can make it kind of modular and switch out with like internal loader system or bucket ladder, depending on what we choose at the time.
Just how mechanical team mentioned, the drivetrain is going to be the same for both the designs. It's just the way excavation and deposition works. That's where we are falling, like we are confused or like not sure how to implement it.
And like we said earlier, that how they measure how much sand we have deposited is that they usually calculate the volume difference. Initially, how much volume was there inside the berm and final volume. So the reason being deposition, that how we deposit sand also matters a lot.
Yeah.
Because sand, once you drop it, it will start flowing. If it flows outside the boundary, it won't get counted. That's why again it's in consideration that which design will be more better for
You have to
depositing.
drop it from a height because it has to be inside.
And
the
it can't be from
Yeah.
a very big height, because then there's a lot of dust.
Right.
So
also, if I don't know how many or who is watching the YouTube live stream, but if you have questions or you think that a certain design is better,
Yeah.
comment and
Should I put up a poll on
Log
YouTube?
in.
can put up a poll.
Log in.
I do think that the internal loader will have less dust.
yes.
Yes, we agree.
Yeah.
We agree.
Yeah.
Yeah, no, I'll agree with that one. That's true.
I did a bit of a review last night on West Lafayette system, and one of the main drawbacks they had for the bucket ladder system was that it produced a lot of dust.
You guys are covered over the storage, so when it comes in, it kind of conceals that dust.
Yeah,
from
that's
the
what
sea.
West Lafayette did. They put a cover over here when it's digging, and then when it's depositing over here, to avoid dust going everywhere.
Of course, they also mentioned that did create a problem with rocks getting trapped.
Yes.
Yeah, but when you put a cover, it's increasing the weight, and weight is.
Yeah. Yeah. So that's another factor we have to think about.
Wait. Oh,
Sorry.
yeah.
Yeah. Can keep some buckets or something to simulate the obstacles. So that would work.
Yeah, I mean, we don't really need a
As
rock.
an autonomous team, our idea is not really to detect if it's a rock or not. it's to detect that we should not go near it.
Yeah.
So
It's any obstacle.
any
Any
obstacle,
obstacle, basically.
and
Yeah, we will be using rocks eventually, and basically what assumption we're doing is, ideal condition is the entire field is flat. If there's any abnormality, we're considering it as an obstacle.
Yes.
So it doesn't matter if it's a rock, a crater, bucket, column, wall. If it's not a flat surface, it's an obstacle for us.
That's why we are using, like, we are asking the CS team to use a very strong AI camera. So even if it can detect like depths and stuff, like, so even it can detect like a crater, for example, because you can't really see a crater from the camera. You have to detect it through the difference in height of the
And also, when sand accumulates, there can be a pile of sand.
pile of sand.
And the robot can get a lower height, so it can detect it as an obstacle, but it is not an obstacle.
now to make the best models for this, what we are doing or going to do is NVIDIA has a software, I forgot its name, but there once you make these models, you can deploy them, the robot in the simulation. It keeps running for a lot of hours. It works on reinforcement learning. So it goes through various edge cases, that if the ground is uneven, if there are rocks, if it goes and bumps into rocks. So the model keeps training on these kind of edge cases. So when we bring it into real life, it should not break.
Self-learning.
Yeah,
Yeah, but
Good, right?
I know it's also it's a new software by
Oh, it's a
NVIDIA.
new-
It's a physics-based software.
Oh, okay.
Oh,
back to design.
Oh, yeah.
yeah. So
Back to this.
which
Got one YouTube comment in promote or in support of the bucket ladder.
I think it's you.
That wasn't me. I didn't ask anyone to comment on my behalf.
I just put up a poll.
Yeah. But do you guys have any preferences?
I think the dean said that he likes the.
No. He didn't specifically.
Seems like you would be able to get more material excavated in the bucket. And it looks like there's many buckets there. So if one of the buckets fails, you can have another backup for collecting more material. Obviously, there's the dust consideration as well.
Yeah.
Yeah. One good one good thing about the bucket ladder is that sometimes the terrain could be uneven. So let's say we are standing at a terrain, the next part of it goes a little bit below the surface ground level. The bucket ladder can go below and dig more sand and then come back and drop it. Whereas the other design, it might miss some
Yeah, because
amount of sand.
we're basing it off of
A fixed path, yeah.
a fixed path that it has minimum room to, for variables, different variables, but
It's basically like how hard coding and dynamic coding works.
Yeah, I think both designs would, to be honest, work fine. It's honestly, much more nitty-gritty stuff, but again, the other thing to consider is the bucket ladder is more power efficient. Just saying. Just saying.
Yeah.
But
Yeah.
Just want to remind everyone.
yeah.
Yeah.
That,
No, that's why we wanted your feedback so we could make a decision.
Yeah,
today
we're-
itself,
we're like a-
today itself, we closed the design chapter, so we
Yeah.
could start with the preliminary design review.
Basically, they took the guns off their shoulder and kept it.
What do you think? Okay.
What do you think?
I'm just a team member. Don't ask me.
It's fine. We have a lot of team members here.
We can get a poll of everyone, including team members. Want to take a poll of everyone, including team members?
That we know already.
Just
I want to see. I just want
the
to
only
see.
thing I
Just
have as issue with the bucket ladder system is relative complexity and ease of production. We'll have to be on the ball with sourcing parts.
That's true. True.
So, how much longer do you think it'll take to manufacture the bucket ladder system, design the bucket ladder system, considering that most of our designs are for the internal living?
I already have some CAD models ready for the bucket ladder as well, so it shouldn't take that long compared to.
To be very honest, once we decide a design, should not take long for the every team to.
So once we have a design, we can focus fully on that one. We won't have to split our focus between the two designs. So that should help us streamline our
And
process.
to be very honest, it doesn't matter with software.
Yeah.
Yeah, software.
We are just trying to get our vote in.
The same way the internal loader has limitations on the actual terrain, like with the predefined path. With the bucket ladder, there's a lot of room for error when developing it itself, rather than if we develop it properly, it can work amazingly on the field. But I feel like it has a lot of room for error. It has way more variables.
The only thing I see is that if there are 10 bucket ladders, 10 good bucket ladders, it's very hard to beat them. We have to do very good in other sectors.
My only thing is that with this design, it has very less movement compared to that. Like it is only picking up sand points.
Yes, if you consider why NASA is doing the competition, they're trying to evaluate a bunch of different excavator designs. So,
And we're trying to win.
Yeah.
I agree. We lose, right?
No, we will.
We'll win, yeah.
Can we get votes from everyone?
Yeah.
Yeah.
Yeah, he already voted.
Oh, we've already got a couple. Yeah.
Yeah.
Option one, maybe.
Option one.
I'll start with you. 1, 2, 3. Option 1? No.
5.
I'm undecided.
5?
Oh, five.
I think then.
We'll count.
Second design.
Yeah.
Antian did not.
It's not that many.
No.
It's not a giant difference.
Okay, I think let's start off with the drivetrain.
No,
Yeah.
no.
No.
The
We decided.
second design got most votes, so we will move forward with the second design. We don't want any more discussions on this.
Now it's the every team to.
Yeah.
If it breaks down, it's not my fault. I'm not taking more. Unless it's electric.
Wait, I'm so confused.
Like, for explaining the people.
I think they'll both work fine. I believe this stuff can be done. But
The main thing is tipping over.
Yeah, we'll.
Yeah.
I don't think that's been explored.
So the conclusion for this system design review finally is that the team now has a proper design to move forward with, which is the internal loader system. So don't think about anything else. Feel free to do all sorts of work on the all sorts of research or internal loader system. I just wanted to thank Dean, Dr. Elfayumi, for showing up to the meeting on such a short notice, especially, and Dr. Antin Wong and John for showing up. Dr. Liu left, but even Dr. Thompson and Dr. Guping Wong joined via YouTube live stream. So I would like to thank all the faculty members and, of course, all the team members to join the meeting. Thank you so much.
Before the end of the semester, so you might get some funding.
Sure. Yeah. We will reach out to like Katie from ETCS, ECE and CS and ME, all of them, so that we could start with the drivetrain.
Also for the space in the ATC.
Yes. Yeah.
Let's get one quick one.
Okay, we were initially having our meetings in liberal arts basement room 35C, which is like a huge space and like kind of like a perfect room for our project.
We have another
We got
vote.
a whole lot of votes.
Oh, we got a lot of
ladder
okay.
from a UK team.
I'm just
Hey,
saying.
virtual votes don't count.
This is a democracy.
This is democracy. Come on. I'm only slightly.
How many people vote?
There were around 10 people watching.
There should be a chat. Somebody